Let's finish up the nonparametric regression. We'll start linear classification. Thursday, Ryan is going to give a guest lecture. I'm still not sure of the topic. Probably something called trend filtering, which, if that's what it is, it'll be a good example of a nonlinear smoother. And then when we come back, we'll finish a nonparametric classification. Then we'll turn back to some general theory, and we'll talk about how do you prove these minimax lower bounds that I keep referring to. So just to remind ourselves, we talked about a few different nonparametric regression methods: kernel regression, local polynomial regression, regularized regression such as splines and reproducing kernel Hilbert spaces. These are what I would call local smoothing methods, and these are regularized methods. But we saw they're all they're all linear smoothers. Kind of a unifying theme. And every one of them involves a tuning parameter, which has to be chosen typically by some form of cross-validation. And then we saw that there's some theory to say that that does a very accurate job of choosing a good tuning parameter. I mentioned that the rates typically have the form, the prediction error rates or the function estimation rates, 1 over n times 2 beta over 2 beta plus d. Beta is commonly taken to be 2, so that's like 4 over 4 plus d. That's bad when d gets big. Because if I want this MSE to be less than epsilon and I rearrange it, you can see that n has to grow exponentially with dimension. And it's a minimax bound, so this is a hard bound. This is just saying that statistically, the problem of prediction for regression gets exponentially hard with the dimension, at least without further assumptions. We'll see that the situation for classification is a little bit different for certain reasons. And this is, of course, based on this minimax theory. But in principle, apart from this problem, everything we said, whether we use local polynomials or kernel smoothers, whatever, can be applied to an arbitrary dimension. It's just not guaranteed to be accurate. Okay. So that's just a review before we go on to the next thing. Any questions? Good. All right. What I want to talk about is a very popular class of nonparametric predictors that are used in high-dimensional cases instead of just applying one of these methods. And in some sense, it's trying to balance. It's basically, you can think of it as adding more bias to reduce the variance, but also it's adding some interpretability. And so I'm on page 15 of the notes here. These are called additive models. You can think of this as being kind of halfway in between a linear model, which has a very, very special form, and a completely nonparametric model where we're just doing some sort of local smoothing perhaps to the whole space, to something in between. And we're fitting a model of the following form. We're going to say that it's a sum of smooth functions. Now, as usual, this will be a working model. We're not going to really assume the truth is of this form, but this is going to be the working model we use to generate our predictor. So you can see if I took m to be a linear function, then of course I get back linear regression. But now we're allowing it to be an arbitrary smooth function, but only of one variable at a time. So this is not as nonparametric as the completely nonparametric thing, but it's more nonparametric than linear models. These are really, really easy to fit. And one of the really nice things about it is it's very interpretable in the sense that I can look at each individual function. If you fit a 10-dimensional nonparametric regression, if it predicts well, that's great, and so that's fine. But trying to picture a 10 or 20-dimensional function is very, very difficult. However, I can just look at these one-dimensional functions, which makes it much better for many purposes. So if you look at there's an example on page 7 where I did a 3-dimensional fit. But instead of having to look at the 3-dimensional fit, this is on some geological data, I can look at each of the one-dimensional functions. In this case, they're not that interesting, but sometimes some of these one-dimensional functions turn out to be interesting. So there's kind of a trade-off here. You're getting some interpretability, but you're adding bias because it's a less general model than the overall model. Now you could ask, is there something in between this and completely nonparametric? And there is actually. You could start to add more terms to this model. You could add two-way interactions. So in other words, you could add terms like this, m1, 2, some function of x1 and 2. And then you could add a function, say, 1, 3, x1 and x3. Then you could add, if you want, 3-way interactions and 4-way interactions and 5-way interactions. And so you could see you could actually build yourself towards a completely nonparametric model. In fact, you could imagine doing a kind of nonparametric forward stepwise thing where you add in these functions one at a time, then consider adding in 2-way and 3-way interactions. Surprisingly, I don't see that area explored very much. I haven't seen much about that. But you could do that. So it's actually a pretty general and flexible framework, these additive models.
Why cannot we add an L1 penalizer?
We'll get, you're one step ahead of me. We're going to eventually do that. We're going to do sparse models. Actually, there should be some sort of overall constant here, just like we do in linear regression. So the real question, though, is in some sense computational. How do I fit something like this? And the most common way of doing it used to be called backfitting. Is the original algorithm. It's really a kind of example of, I'm forgetting the name, you know, when you have a multi-dimensional optimization, you optimize one variable at a time and you repeat. Not alternating. Coordinate descent. Thank you. It's like a type of coordinate descent. I just was blanking on that name. But it's not clear always whether this converges or not. So there's some theory on this about convergence, but I think there's a lot of open questions. But the idea is this. Suppose you've already written your code to do one-dimensional smoothing. Hopefully by now you all have. If you haven't, that's worth doing. It's pretty easy. Pick your favorite one-dimensional smoother, whatever it is. Write some code in R, maybe MATLAB, but hopefully R. And the idea is now just to create a loop and smooth these things one at a time. So this is the algorithm on page 16. So first of all, the overall constant, let's talk about that. There's what's called a non-identifiability here, which is if alpha, I could have 5 plus, let's suppose this was alpha was 5, and the function m1 of x1 was just some smooth function. But I could just as well as define the constant to be 10 and take the function, just redefine m of x1 minus 5 to be the function of x1. And of course, these are the same function, right? So there's a sort of indeterminacy between absorbing the constant into one of the functions, if you want. So it's a little bit, it doesn't matter. It's just arbitrary. We just arbitrarily get rid of that problem by insisting on some sort of constraint. And so the usual constraint is we'll just take this, we can take it to be any constant. Usually it's taken to be y bar. But then we should make sure that these things always sum up to 0. Okay, for those of you who have taken analysis of variance, it's exactly the same thing. That you have a bunch of columns of data. There's an overall mean and there's the individual treatment means. You have to decide on a parameterization. So there's it doesn't matter how you do it. The final fitted function is going to look the same, but for algorithmic purposes, you have to decide how you're going to handle this. So we're just going to always take y bar to be alpha. Okay, and we're going to estimate these things. And the way we're going to estimate them is one at a time. We're going to do like a coordinate descent kind of thing. So what we're going to do is we're first going to take, so let's take initial estimates. M1 hat to MD hat. Now, what are these initial estimates? Different choices can be made. Some people take the 0 function. So they set these equal to 0. Some people will take a linear fit. Some people will take a one-dimensional smoother. There's a lot of different choices here. And now what we do is we're going to update them one at a time. So I want to update m hat 1. So what I do is I take the data, and I take the current fit, and I subtract it out. So I take yi minus the current fit. So that's going to be alpha hat plus all the other functions. So this will be the sum of mj hat of xi for j not equal to 1. Okay, so I'm just taking y minus all of this except for m1, which is the one I'm trying to estimate. So I'm getting these residuals. Let's call that. And now I apply, let's call it smooth. You've written your code, which takes, we're going to assume you have some function, smooth, which takes some y and some x and produces m hat, whatever your favorite smoother is. So we'll just apply it here on these residuals and on the variable x1. So I'm just taking what's left over after I remove all the other functions and smoothing that on x1, on the first, I should really write it like this, x1. That's going to give me a new m hat, m1 hat. Okay, now I do the same thing for the second variable. I take ri to be yi minus alpha hat plus, and now I just subtract all the functions, including the new m hat, m1 hat, for j not equal to 2. And then I take m hat, you just apply your function to the residuals and x2. Okay, and then you keep going until you've refit all of the functions m1 hat, m2 hat, and d hat, and repeat. And hopefully that'll converge. Otherwise, if it doesn't, you have to have some sort of stopping criteria. Stop after 10 iterations, stop after some convergence criterion. Most of the software in R will give you a warning if it doesn't converge. It's pretty complicated, and it's very dependent on the smoother you're using. So for some smoothers, there's theory worked out about convergence. For some of them, it's not known. One thing I have to say, though, is remember this non-identifiability problem is after you get the m hat, you should always replace m hat with m hat minus the average. Did I put that as a step in there? Yeah. So like when you're doing mj hat, remember you want it, you fit it, and then you have to make sure it averages to 1, or to 0. So you subtract out that constant. Just subtract out the constant again so that you don't have this identifiability problem. So every time you do it, get the m hats, make sure they average to 0. If they don't, just subtract out the mean. And that's it. So apart from the questions about convergence, I'm not sure what the state of affairs is right now. So I'm not an expert in optimization. I guess in the convex optimization class they discuss this. And there are conditions that will tell you when it converges and so on. In practice, you may get warnings that it's not converging. Typically, I think if it's low dimensional, you don't usually have convergence problems. You will have problems when it's very high dimensional, but we're going to get to the high dimensional case. We want to do something different in that case anyway. The nice thing about this, though, is code-wise, all you need is any one-dimensional nonparametric regression method, and you put a wrapper around it, and now you have a d-dimensional method. There is a question, too, though, about smoothing parameters, is that do you use a separate smoothing parameter for each function or one common smoothing parameter? And probably, if we had a lot of computing time, I would say a different smoothing parameter for each function. That's a lot of work because then you have to do cross-validation over d different smoothing parameters. So I think in practice, people often use a common smoothing parameter, so there's only one smoothing parameter to pick, but that may or may not be optimal. Probably not optimal. So there's a trade-off there in computing time and optimality. But this is a very, very, very common thing. This is another example of something where I'd say in statistics it's probably the most commonly used multivariate method, whereas in ML not so much. And I think a lot of it depends on whether you want interpretable fits or not, too. But remember, at the end of any of these fitting procedures, I should have said this, if you have lots of data, hopefully you do, it's always good to keep some holdout data so that at the end of the day, you can see whatever method you've chosen, how well it works in prediction. And so you really still want to check whether this is predicting well or not. It may predict well for your problem. It may not be. An additive model might not work well for your problem. So hopefully, if you have enough data, you can always have some holdout data to check the prediction accuracy. If it does work well enough for what you're doing, it is simple and it's interpretable and so on.
For generative models, do you still use the same idea of holdout data?
For generative models, Well, are you talking about regression or?
Any type of generative models.
Well, so now let's come back to that question. I mean, that's a sort of a general question about evaluating how well a generative model fits the data. Is a very, very big topic. I would always try to have some hold data if I can. I mean, of course, it depends how much data you have. Yeah.
So, I mean, when you say like fit using the smooth function, it wouldn't do anything, right? Because for non-parametric stuff, there's nothing to be done.
Sorry, I didn't get the question.
I mean, when we do non-parametric fitting, there's like nothing to be done, right? We only like need to compute things when we need to find the value at some place. There's no parameters to find, right?
Well, you have to, at each stage, you're doing, say, a kernel regression.
Right. But
And that's going to involve say, like a bandwidth,
okay. Oh.
right? There's usually a tuning parameter. Well, there's always a tuning parameter in these things.
And finally, you will use cross-validation to choose
The tuning
optimal
parameter. Right. That's right.
So, I mean, is there not something sort of in between just sort of arbitrarily picking a common tuning parameter and doing it for each particular feature? I mean, is there some way of looking at the bivariate relationship between each of the features and the target variable and heuristically picking a
Yeah,
variable?
you could do that. So you could just do marginal smooths of y on x1, y on x2, y on x3, and try to pick an optimal tuning parameter for that, and then use that throughout this algorithm. There's no guarantee that's really what's optimal for this, but that might be a good compromise, actually. Yeah.
What's the kind of intuition when you are just subtracting the average on the m hat?
Well, it's this problem of identifiability is that, again, I could add a constant and subtract a constant here. So there's really an equivalence class of solutions. And I'm just picking one. And the one I'm defining to be the one that we're choosing to work with is the one where these average to 0. There's nothing special about 0. I could have picked these average to 32. As long as you're consistent about it, you're never going to converge to anything if you let these wobble around back and forth in your algorithm. So it's just a matter of, there's really an equivalence class of solutions, what part you put into these functions and what part you put into this constant. And you have to be consistent about how you do it whenever you run some sort of algorithm. The final function doesn't care, right? Whether I make this 0 or y bar or whatever.
So you need to like keep the function to be the average on the training data.
Yes, so that's just an example. You need some constraint. So the most common constraint is let's make the average 0 on the training data.
Do you immediately use the new value of m hat after the
Yeah, the usual thing to do would be when I'm fitting the next one, I'm using the new updated version of m1 hat. Right.
Is this algorithm sensitive to the choice of initial estimator?
It is because, well, that's the same as asking what do we know about the convergence properties, right? If we knew it converged and we knew it converged independently of how you choose the starting functions, then I could say it doesn't matter which starting functions you pick. But again, I'm not sure that the theory is completely settled there. That's something you might want to ask since Ryan's going to be here Thursday and he's an expert on optimization. You might want to ask him about, use the opportunity. Ask him about what's known about convergence theory for additive models. He's actually been thinking about additive models lately, so I know he's thought a lot about this. Okay. So this is some built-in function in R. It's called GAM, Generalized Additive Models. I can't tell you what the corresponding thing is in MATLAB, or even if there is one. Maybe does anybody know? Is there a built-in thing in MATLAB? Does anybody know? Don't know. Okay. Writing your own, though, as you can see, is pretty simple, right? If you just put a wrapper around any one-dimensional smoothing method, you automatically have code for doing this. That's one of the nice things about it. So, yeah.
And R just uses linear smoothers, so there's no nonlinear smoothing.
Can you use any smoother? Any smoother.
smoother.
Yeah. Put your favorite smoother in here.
So it's a higher level.
It's a higher level idea because you could be using kernel smoothers, reproducing kernel Hilbert space smoothers, nonlinear smoothers, wavelet smoothers, whatever your favorite smoother is. Right. Okay, so that's one way of dealing with high-dimensional data. This is not to say you couldn't try one of these other methods on your data, and maybe you'll get good predictions. You know, you can estimate the risk with cross-validation. You could even do both and try to choose the one that has the lowest cross-validation error, for example. Now, this is all well and good, though, when D is pretty small. When D starts to get really large, we're back to sort of the same kind of problem we had for linear regression. Like you know, we can't do linear regression when D is bigger than n. How are we going to do a sum of non-parametric functions when D is bigger than n? So you asked about an L1 penalty. Yes, there's an L1 penalized version of this where the penalties are on the functions. Okay, so this is called spam at least in the notes. This is something many years ago I wrote a paper with John Lafferty and Pradeep Ravikumar and Han Liu about this. We thought this was a pretty clever name, sparse additive models. And you might wonder when we were emailing each other, did our email end up going in the spam filter? The answer is no, because people who are trying to send you spam are at least smart enough to not use the word spam. And the way to think about it is, you could imagine, there's different ways to formulate this, but we're putting some sort of penalty, you know, in linear regression. Whoops, it looked like that. You might guess it would be the same for the functional case. It's actually a little bit different. The correct penalty is the 2 norm of the function. Now that might seem counterintuitive. Why the 2 norm? But this is really the 2 norm of beta j. Right? That is, what's the 2 norm of a scalar? It's the absolute value. The difference between L1 regression and L2 regression is really whether the norm was the norm or the norm squared, is the way to think about it. And it turns out all of this, for doing the functional case, it's the fact that we're not using the 2 norm squared, that the 2 norm is still like we're taking an absolute value. That's going to be effectively the penalty function. So the way I wrote it, there's different ways of writing this. So the way I wrote it in the notes was, we're going to write down again a working model, j equals 1 to d of functions. I switched from m to g for some reason, so I'll follow the same thing here. Again, we need some sort of constraints for this to make sense. Even now, we need, you know, like for example, not only with the alpha, but I could multiply this by 10 and divide this by 10 without changing anything. So in order for this to be a well-defined problem we're going to deal with, we're going to require that these things have mean 0 as we did before. So gj, xj has mean 0, but we'll also take the second moment to be 1. It doesn't matter. You could make it, again, to be 52 or whatever, as long as we're consistent about it throughout the algorithm. Otherwise, this beta j wouldn't be well defined. And now we are going to put, if we write it this way, we're going to have this sparsity constraint on the beta j's. But again, that's, in terms of functions, that's really like putting a condition on the norms. And in fact, you'll notice I re-expressed it. So that might be the way to, I'm trying to link it here with the L1 stuff that you're used to. But if we now write it in terms of functions, we actually get the following algorithm. Minimize over all functions mj in some space. I'm going to write hj, but it doesn't have to be a reproducing kernel Hilbert space. It's just some smoothness restriction. This is a way to think about what we're trying to do here. We're trying to minimize y minus mj of xj squared. So I'm writing down the population version of the sparse non-parametric problem, subject to the mean of these MJs being 0 for identifiability. And again, the expected value of MJ squared, this is the norm, square root being less than or equal to some constant. That's the sparsity constraint. It turns out that the solution to this sets some of the functions equal to 0. Right? The property we want is we want to set some of the whole functions equal to 0. This is the problem we'd like to solve. And one way to solve this is to solve it in a coordinate descent way at the population level, and then substitute the sample versions. And here's the nice thing about this. You get back exactly the same algorithm with one small change. You run this algorithm, so the sample, the minimization has a well-defined form if we write it out in coordinate descent version. The sample version is exactly this with one extra step at the end, which is to sometimes take the MJ hat you've computed and set it equal to 0. And when do you do that? So this is not arbitrary. I'm saying this arises from writing down the optimization problem. Here's what you do. You first get the MJ hat at each step. And now you do something called soft thresholding. How many of you heard of soft thresholding? A few of you. Soft thresholding, this is soft thresholding. This is the soft thresholding function. You give me a real number, and I evaluate this function. And you can see what this function does is it makes the real number closer to 0. And for some values, you actually get 0. So it's written like this. It's actually equal to 1 minus lambda over, why did I call it PJ? It should be, yeah, I wrote it out kind of abstractly there, but anyway, this will be let me write it like a, we get the original MJ hat. So that's just running this algorithm. Now you compute this average squared value of this thing, and you take lambda over that, 1 minus that, and the plus means if this is negative, you set it equal to 0. So A plus is just the maximum. What that's saying is that in some cases, this whole function is going to get set equal to 0. This is basically soft thresholding the function. It's doing it to a whole function instead of a real number. And that's called spam. All it is an additive model with a sparsity constraint. And I didn't put the details in here. You can look up the reference, but where this comes from again is we're trying to minimize the sums of squares over additive functions subject to this functional sparsity constraint. And the solution is run, or at least an algorithmic solution is run backfitting, but at each stage shrink it according to this criteria, which might end up setting the function equal to 0. And so just like the lasso sometimes sets the beta j hats equal to 0. In fact, one thing we didn't talk about, but I think I put it on the home. Didn't I put soft thresholding on the homework? I put hard thresholding. Okay, it's going to be on the next homework probably. I have this vague recollection of describing this. Let me just tell you that in the lasso, the solution's kind of complicated to the lasso, but there's a special case where the solution has a closed form. And that's when that design matrix has orthogonal columns. If you have a low-dimensional problem, and if the design matrix, if X transpose X is the identity, that's called an orthogonal design. Okay, you don't get these very often. They usually come from designed experiments, and the random data aren't going to usually satisfy this. But if it does happen, it turns out that you can write down the beta j hat is simply equal to the least squares estimator with the soft thresholding. So let's call it beta j hat least squares minus lambda if beta j hat least squares is less than minus lambda, is bigger than lambda. This is this function I'm writing down. 0, and then beta j hat least squares plus lambda. If beta j hat least squares is less than minus lambda, and this is the case so let me just repeat what I'm talking about. In special cases, very special cases, you can write down the lasso estimator in closed form. And it basically comes down to applying this thing called soft thresholding, which is you take the least squares estimator. If it's close to 0, you just set beta j hat equals to 0. Otherwise, you shrink it towards 0. That's a special case when the lasso can be written in closed form. That's all we're doing here. It's really just a functional version of that. It's saying that when you estimate the function, and if its norm is close enough to 0, you set the function equal to 0. Okay?
Is it possible to save some computations? Because right now you are actually, it's only kind of like true or false, right? So it's whether this whole thing is positive or not. So since it is step 4, is it possible to save some computation, like from 1 to 4, like by estimating whatever that is in the bracket?
Well, estimating this comes from the function estimate. You want us to be able to decide ahead of time whether oh, well, that's an interesting question. So could we actually figure out whether to set mj hat equal to 0 without going through all this? There is work in the lasso on that called safe thresholding. There are things called safe thresholding rules which try to, that try to rule out ahead of time that you don't need to consider certain values. So maybe it can be done in the non-parametric case too. I don't know actually. Yeah. The good thing though is if you've already written code to do this, it's one extra line of code really to do this thresholding thing. Now there's an extra parameter to pick, however, which is lambda, which is just like in the lasso, the sparsity. Okay, and I actually wrote down for you the GCV, the generalized cross-validation estimate for picking lambda, but I have to tell you, this is a heuristic. It's never been proved that this is a good way of picking lambda, minimizing this quantity. So there's a lot that's not known theoretically about this. There's been quite a few papers now about sparse additive models. But there's kind of a gap between theory and the practice, but it is pretty useful. So let me show you, I just want to show you some examples of what ends up happening when you actually do this. The whole algorithm is written for you there at the top of page 19. So first of all, here's some synthetic data. This was 190, this is on page 19 now, 150 observations, but 200 functions, 200 features we're fitting. So we're fitting a 200-dimensional additive model. Now, we generated this model, so we know the truth, and the truth is given there. There's 4 functions that are, one of them is a sine function, then one of them is quadratic, and so on. And then the other 196 are 0 functions. Of course, the algorithm doesn't know that, but that's how we generated it. And the next page shows you kind of the output. It's a little bit hard to look at. I didn't know how to squeeze it all in here. So if you turn this one this way, all this is showing you is actually, now that I say this, I forgot to mention this in the lasso. When you're fitting the lasso, one good thing to plot, I'm going to put 1 over lambda here. So when lambda's big, you get a sparse model, right? So all the coefficients are going to be 0, and then it's going to go less and less sparse this way. And remember what ridge regression looked like. Ridge regression, you had these smooth curves that were never equal to 0. What happens is if I plot beta 1, beta 2, beta 3, beta 4 as a function of lambda, each one is going to be 0 for a while, then it's going to become non-zero at some point. Beta 2 might look like this. You know, beta 3 might not come in till later on. This is what a typical plot looks like for the lasso. It's always a good idea to do this. Plot your coefficients as a function of the smoothing parameter. And by the way, in the lasso, it turns out they're piecewise linear functions. So this just shows you how the sparsity is happening as you vary the tuning parameter. And that's what this plot is, except here I'm just plotting the norm, the L2 norm of each of the fitted functions. And you can see the 4 functions that are truly non-zero, their norm is very large. And all the other functions have small norm, which is what you'd expect because they're actually zeros. And then the second plot shows the generalized cross-validation for what lambda to pick, and it has a very nice minimum. And when we pick that minimum, now we're going to show you some of the plots of the functions. Now there's 200 functions. You don't want to look at 200 plots. So the first 4 are M1, M2, M3, M4, and what's plotted there is the estimated function of the true function, which is pretty accurate. Then all the other functions are 0. They got zeroed out. Now they don't have the other 194 of them. That would be kind of boring. Just showed you a couple of them. So that's just an example to show you what kind of output you're going to get. You're going to get a whole bunch of 0 functions. You're going to get an estimate of the risk as a function of the smoothing parameter. Don't forget, though, there's a tuning parameter you have to pick as well. And so on. All right. So that's an example of one way to deal with high-dimensional nonparametric regression. Yes?
So the choice of the smoother isn't that important?
The choice of the smoother, how important is it? Probably not that important. I think once you get to high-dimensional situations, that's kind of a second-order consideration, I would imagine. I can't prove that, but probably it's much more important as how much sparsity you pick and how much smoothing you do overall. Those are probably the 2 most important things. Actually, let me tell you another. It's not in the notes, but here's another way you can do this. It's kind of computationally heavy, but it's pretty simple, which is what you could do is for every variable, put down a bunch of basis functions. Pick your favorite basis, cosines, splines, whatever basis you like. So imagine that for x1, I create, I don't know, let's say 1, 2, 3, 4. I'm going to put 5 basis functions down arbitrarily. So this is like, so what I'm writing down here is 1, 2, and this is some basis function for x1 evaluated at the end data points. And this is the second basis function and the third basis function. Okay. Now this is all for the first feature. Now put in a basis for x2. Could be the same basis, could be a different basis, and do the same thing for x up to xd. And now think of this as your x matrix. This is some huge x matrix now, right? It's going to be, the size of it is not only d, but d times the number of basis functions. Now run the lasso. Just fit a linear function of all these basis functions and use the lasso to keep it sparse. That will also give you a nonparametric linear smoother. Well, not linear, but it's a sum of basis functions. And it's going to be, hopefully it's going to adapt in the sense it'll pick out the ones that it needs. It might include some variables from here, some for here. It might leave out x3 altogether. Okay, that's another possible way of doing sparse additive models.
So these basis functions are orthonormal?
They don't even have to be orthonormal because we're using the lasso.
So that will take care of that.
Yeah.
So this is sort of a general question, like to apply to nonparametric or just lasso in general. But at what level of dimensionality compared to sample size would you switch from just doing something standard to some sort of sparsity constraint? You know, curiously.
Yeah, so when do you really need to include some sort of sparsity constraint? That's a very tough question to answer in general. It's part of the art of data analysis, I guess. Certainly when d is bigger than n is an obvious answer. For linear regression, that's probably the answer. For nonparametric regression, I think it's very unclear. I think that's something we don't really know the answer to. I wish we had a diagnostic that would tell us when to do that. You might hope that if you just, that maybe if you always did something like spam, it would tell you. If it doesn't zero out functions, you don't have to worry about sparsity. But there's really not a lot known. So yeah, it's hard to know what to call in practice the high dimensional regime and the low dimensional regime, but it's certainly true in non-parametric regression that it comes up much faster than in the linear regime. Probably in practice, I start by fitting a linear model of some kind, and I check how well it's working. And if I'm getting accurate predictions, I declare a success. If it looks like it's not working well, I'll try additive models, sparse additive models. So there's a lot of fooling around with the data, and that's why, in my opinion, whenever possible, you always want to keep holdout data again that doesn't get touched throughout all of this stuff, because otherwise you never have a clean estimate of your prediction error at the end. Which is easy to say if you have lots of data. If you don't have much data, things are not so simple, obviously.
How would we compare linear regression with non-parametric?
You can compare them just by their prediction error.
No, I mean like more subjectively. I mean, why would we use linear?
Why would you use linear versus non-parametric? Well, if you care about prediction, it is just whichever one predicts best, I think. But linear is easier, and so I always start with the easiest thing. Start easy before you start doing complicated. That's a good general rule. I should say that at the beginning of the class. I see people get a data set and start doing deep learning and a support vector machine before they've tried like linear regression or logistic regression. I always start with the simplest tools first before you plunge into these complicated things.
Maria, I want to ask you on this actually.
Oh,
So
okay.
if you start with a simple model, you build something that works on small data set, and then when you upscale it, that causes a lot of problems. So sometimes you have to reinvent everything again.
It's true that what worked on some small data set, then all of a sudden you scale it up, everything may have changed now, right? It may not predict well anymore. It may not be computationally feasible. So these are just difficult questions, and that's why you're going to earn big dollars when you graduate. All right, let me mention quickly, to finish this off, a couple more items. And when I finish the non-parametric regression, of course, you understand there's a million other methods, right? There's just so many methods out there. I'm trying to cover what I consider to be the most popular and most useful methods. Another class of methods, you're probably more familiar with this from classification, but they can be used for regression too, which are trees. Classification and regression trees. So the very first program that I'm aware of was written by Leo Breiman and I'm blanking out on who else was on the paper. Leo Breiman was an interesting guy. So he was a mathematician, did probability theory. He wrote a beautiful book on probability theory. And then one day he said, all of this academic stuff is bogus. And he just quit, gave up tenure, and worked as a statistical consultant for many years. And then he came back to Berkeley, and he was a completely different person. He developed CART, classification and regression trees. He developed bagging, some of you have heard of, random forests. He just believed in just create algorithms and see how well they predict, and that's all we should be doing. And he had a very, very strong philosophical viewpoint that he rejected all his past mathematical excursions as being useless. He was a very interesting guy. He only passed away a few years ago, actually. In fact, there's a wonderful article by him you might want to look up called Prediction and something else, The Two Cultures. And it's just more of a philosophical essay about his views on statistics and machine learning and so on. Yeah?
What was his name again?
Leo Breiman. You can find his biography too, because it's worth reading. He's just led a very interesting life. I'll tell you a small anecdote. As I was at a conference once with him, and I decided I had to take a break from the talk, so I went outside, and there was Leo, and he was puffing away on a cigarette. And I said, wow, you used to smoke? I thought nobody smoked anymore. He goes, I quit smoking when I was like 40. But I told myself, if I live to be 70 years old, I'm starting again when I'm 70. And he said, damn it, when I turned 70, I started smoking again. So there was a man of convictions. He really believed in this thing. Anyway, I'm going off topic here. So classification and regression trees. This is a really, really good tool, and when we talk about prediction in particular, we'll talk about a generalization of it that some of you may have heard of called random forests. But it's beautiful for being simple and interpretable. I want to emphasize again the interpretability aspect of some of these things, because it's great if you can predict well, but having something interpretable really can be very useful so you understand what's going on. And so that's one thing I like about additive models. Trees have the same property. So for those of you, I'm sure most of you have seen some sort of tree, but maybe not everybody. So let's remind ourselves how they work. Let me just do a two-dimensional tree. So let's suppose we just have x1 and x2. And what we're going to do in the regression version is just fit a piecewise constant, like a histogram. We used histograms for density estimation. Here we just take a histogram, but we just average the y values. But in a tree, you pick a variable first to split on. Let's say x1. And so our first estimate of the regression function is we take the average of y over here, let's say y bar 1, and we take the average over here, y bar 2. And so you can think of this as a piecewise constant. But we can also represent it as a tree because I took x1 and I split at some number. Let's say this was 50. So this is, say, less than 50, and this is bigger than 50. And there's various criteria. How do we choose which variable to split on? And how do we choose where to split? There's various criteria, but a typical thing would be to compare, let's say, for example, let's just say the training error would be the simplest one. What's the training error? When I split, now I have an estimator, and I can compute I have an m hat, which is a piecewise linear function. And I could just look at yi minus m hat I squared, for example, is one criteria I could use to decide. That would be to help me decide not only where to split, but what to split on. And then you proceed in a greedy way. I could now, maybe I'm going to split, say, on x2. So I'll split here. I'll put the split here. So now I have a stepwise function, which is the average of the y's here, the average of the y's here, the average of the y's here. And this was on this side of the split. So here I split on x2, maybe when it was less than 30 or bigger than 30. And maybe over here I decided to split on x1 again. So over here I have a split on x1, taking certain values, and so on. And you keep splitting. And of course we could have hundreds or thousands of variables. So it could be we're splitting on x1, then x5, then x18, and you get this tree. The main tuning parameter, though, is how far to go down in the tree. So now you would do some sort of tenfold cross-validation to decide you can prune your way back up the tree and estimate the prediction error with, for example, tenfold cross-validation. So the depth of the tree now becomes the tuning parameter, the complexity of the tree. And at the end, what you have, you can either think of it as in the feature space as just a piecewise constant regression function, or you can think of it in terms of this tree. And at the end of every leaf, we could have what y bar is here. That would be this would be m hat 1, this would be m hat 2, m hat, however many leaves there are of the tree. And there's code in R and MATLAB for doing this. It's very fast. I'm sure the one in R does the cross-validation for you. I'm sure it does in MATLAB too. But the beauty of this is it handles a lot of problems. For one, it handles the visualization problem. You can kind of look at the thing, right? I mean, this shows you what's going on. Oh, we're splitting on x1. You can see, I split on x1 quite a few times, that maybe x1's an important variable and so on. You could even give this to a doctor, right? Not that I'm trying to insult doctors, but you could have a physician say, oh, let me measure your blood pressure. Now I measure your weight, this. OK, here's my prediction of what's going to happen to you. So it's simple enough that any user could actually use this estimator. And they actually do work well, although as we'll talk about when we talk about classification, there are tweaks of this which actually work even better, which has to do with random forests and things like that. But this is really a beautiful, simple approach. Another thing is it's doing variable selection in some sense automatically for you, because if it never splits on a variable, that's telling you that that variable is not an important predictor in this problem. Also, if there's missing data on some variables, that's OK, because if it never splits on x8, it doesn't matter if some values of x8 are missing and so on. So there's a lot of practical advantages to classification and regression trees. Unfortunately, the truth is they're not theoretically well understood, and this will become even more apparent when we talk about random forests, which are more complicated than trees, that there are theorems about the behavior of trees, but the conditions under which the theorems are proved do not match how the algorithms are run. So if you look at the theorems about, I even put one of the theorems here, but the truth is that's not about how it's actually run. A lot of the theorems make restrictions, like for example, there's some nice theorems that say if you only did dyadic splits, so you only split always halfway, and if you could try every possible tree and choose the best one, then you can say the following theoretical properties. But nobody fits a tree like that. In practice, it's done in a greedy way, right? We don't try every tree. One of the nice things about this is it's greedy, so you can do it quickly. And the splits are rarely required to be simply dyadic. So there's a bit of a gap here between trees, how they're used in practice, and the theory. There is theory about the trees, but I'm just saying that there's somewhat of a gap. I put a simple example here on page 24, which pretty much looks like the one I drew on the board.
Could you sort of think about doing like some sharing? For example, if two splits are like next to each other, maybe they can sort of, you expect them to be close instead of just taking like the average.
Well, that's in some sense what random forests do. So we'll get to random forests next week, but we end up generating many trees and averaging them in some sense. And that's exactly what it's trying to do, is blur the boundaries between them, because you're right, having sharp boundaries tends to add variance to things. And so there's something called bagging, which is called bootstrap aggregation, which we'll see is a way of blurring the boundaries and reducing the variance. Yeah, so we'll talk about that. Yeah.
It seems that these would also become hard to interpret once you go beyond a depth of, say, 30 or something like that.
Well, it's true. When I say they're interpretable, if I did hand you a tree that took up this big of page, you're right, that maybe it's questionable how interpretable that is. But there's still something kind of simple about it, in terms of understanding what it's doing. But yeah, interpretability is kind of a subjective notion. So whether it's how interpretable it is perhaps open to question in some cases.
What about we try mod-varied speed? Mod-varied. I always split over.
Well, that's the great thing about this, right? This is for high-dimensional multivariate things, at least in principle. There's nothing to stop you from doing this in a high-dimensional problem. Right?
How do you solve this greedy optimization? Since you can split at any variable at any points.
I don't know. As far as I know, it's not a hard problem, and it's done very quickly. I don't think you need any special tricks. But I'm not an expert on the optimization. But as far as I know, it's not a hard optimization problem.
It's not exhaustive?
This is never an exhaustive search. The number of trees is large beyond imagination.
Not on every tree, but on every split.
Oh, yes, it is exhaustive. So most algorithms, I think what R does is it just tries these values. I think. I haven't actually looked at the code to see what they're doing, but.
I think they just try all the training points.
Yeah, you don't need to. Obviously, not going to change anything in between training points. So there's only a finite number of points you have to try. That's true. Equation 21, sorry, page 21, equation 44. There is a typo there. That would be 0. So this is just saying, this theorem is just saying that piecewise linear estimators under a Lipschitz assumption have a certain bias and variance. I didn't go through this, but I did write down m of x minus m of x, which would be uninteresting. One of those should be a z, m of x minus m of z. Thanks. Okay. How many of you have tried trees? Yeah, quite a few of you. They're a pretty popular tool. Okay, the last thing I want to talk about, so I'm not going to keep going on and on about different nonparametric predictors. But I do want to mention something about inference and a kind of subtle problem that comes up here. What do I mean by inference? I'm talking about standard errors, confidence intervals, things like that. Do we need those things for nonparametric regression? Well, it depends what your goal is. If all you care about is prediction, no. Then all you care about is getting out the prediction. Who cares what any sort of inferential statement is? So if you're doing a pure prediction problem, you get your predictor and you're done. That's all there is to it. But if you're trying to do something where you're trying to have some sort of scientific understanding about how things are related to each other, you might want to have like a confidence interval around an estimated function, standard error, something like that. Let's go back to one-dimensional function estimation. You know, if this was some, scientific thing, like we talked about the bone mineral density example at the beginning, there's some true function we're trying to estimate, and we have some estimate, m hat, and, in 705, I pounded into your heads, never provide an estimator unless you provide at least a standard error or confidence interval, so we have some notion of the accuracy. And it turns out that if for nonparametric problems, this is a very, very tricky problem. In fact, in some sense, it's an impossible problem. Let me explain why. Suppose I just even wanted to pick a point. So first of all, you'd really like to have a confidence band rather than just at a specific point. But that's solvable using the bootstrap. We talked about the bootstrap 705, and we'll talk about the high-dimensional bootstrap later in this class. But let's forget about that. Let's just concentrate on one point even. Can I put a confidence interval around m hat? Here's the problem. How did confidence intervals work? Well, typically, we were relying on facts like in 705, like this was converging to a normal with mean 0 and some variance. And that was kind of the starting point, with some sort of convergence and distribution was what allowed us to get some sort of confidence interval. Can we do a similar thing here? Well, watch what happens. Here we have the problem which I call we're victims of our own success. Here's what I mean. Suppose I look at m hat minus m at a particular point. Let's ask, does this converge to something, maybe a normal distribution? Well, remember that this is a random thing, so it has a mean. So I'm just going to add and subtract the mean here, which is m hat minus its mean plus root n, the mean minus the truth. Okay. Now we should also divide through usually by some sort of standard deviation. So let's just say we have, just to make life simple, suppose I even told you the standard deviation of m hat. Let's just to eliminate any complications. So I'm going to divide through by the standard deviation. So that's like dividing through by sigma here. Okay, so let's look at these quantities. M hat is some sort of, complicated thing. It's a ratio of sums and so on. But by the delta method, we would expect this to have a normal distribution. Now there's a complication, which is there's a tuning parameter h, and that tuning parameter is going to 0. So everything's kind of changing with n. However, it turns out the central limit theorem still applies. It's not the same central limit theorem we did in 705 because of the changing bandwidth. But nonetheless, the central limit theorem does apply. And so this is good. Under pretty weak conditions, this converges to a normal 0, 1. Okay. But the problem here, in fact, I shouldn't have, this, what is this? Well, actually, let's look at this term. What is this term? That's the bias. And this term, variance, or standard deviation. If I squared this, I would basically have bias squared over variance. Now, in parametric models, we never talked about this because in parametric land, it turns out, I never told you this, the bias is always of small order than the variance for maximum likelihood. Well, not always, but for typical problems. And that term goes to 0. But remember, if we're really good at nonparametric prediction, what are we going to do? We're going to balance the bias and the variance. That's exactly how we're trying to choose the bandwidth, right? Is we don't want the bias or the variance to dominate. What does that mean? This term is never going to go to 0 as n goes to infinity. If you're doing a good job, Your reward is that this does not go to 0. That means that this whole thing is going to converge to a normal with some mean 0 and some unknown. Sorry, not the problem is that it's not mean 0. It's I've divided through by the variance. There's some bias. What that means is that your confidence band is centered around the wrong function. In fact, you can try this. Do a simulation and just do the delta method. And what's going to happen is, and do something where you know the truth. What you're going to see is, here's the true function. Your confidence interval is going to look like this. It's going to be centered around the wrong place. This is not a theoretical thing. This is what actually happens in practice. That we can't really get a confidence interval because we've balanced the bias and the variance. The very thing we're trying to do is to help us predict well makes it hard to do inference. There's this tension between inference and prediction. So what do you do about this? One of them is, one thing you can do is say it's a biased confidence set, too bad. It's really a confidence set not for the true function, but for the mean of the estimator. And you could take the point of view, that's just the best you can do, and you just live with that, and that's probably the most common solution. Okay? So it's a little bit off. It's life. That's one solution. That's the easy solution. There are other solutions people have attempted, but they're pretty difficult. You could say, well, how about if I estimated the bias and subtracted off the estimate of the bias? You can do that, but now you've increased the variance. You've destroyed your bias-variance trade-off. And now you are going to get good confidence bands centered around a suboptimal predictor. So it gets kind of complicated.
Does it make any sense to generate a confidence band from the low biased predictor and see how the bias, but the reduced risk estimator fits in that confidence band with the unbiased predictor?
Yeah, so undersmoothing is one thing you can do, which is people will undersmooth, which reduces the bias. The difficulty there is how much do you undersmooth? I mean, it's treacherous territory because it's not clear how much to do it. And I would say that's an example of something where there's the ratio of the number of papers divided by the number of people who do it in practice is huge. I think most people just, did you get that? So I think it's an interesting problem, but I think in practice people just tend to ignore it. I just wanted you to be aware of it, so that if you go ahead and construct some sort of confidence set, just be aware it might not be centered around the true function. It's just a warning. And it's kind of an interesting fact about nonparametric estimation.
So in complex problems, especially if we do this method, can we expect the confidence bands to blow up?
No, they don't blow up. Oh, that's a different problem. In high dimensions, what do the confidence bands look like? They tend to be wide. I think that's what you mean. But that's correct, because that's a correct reflection of the uncertainty we have in high dimensional problems.
Isn't that going to be the same consequence if I do this undersmoothing?
Undersmoothing will, no, undersmoothing will reduce the bias. It will increase the mean squared error of your estimator, of your predictor. That's different than talking about the width of the confidence interval.
But I mean, if there's more about variance.
Well, there's another trade-off now, which is the trade-off of how much bias there is in the confidence interval and how wide is it, which is why it starts to get complicated, because now there's another trade-off you have to deal with.
So variance and the thickness of the confidence band aren't.
Oh, no, it is there. You're right. It's going to increase the width, yeah. I'm not really suggesting that you should do much about this. I just wanted you to be aware that there's how to interpret the confidence interval. The most important thing is whatever confidence interval you construct, interpret it as the safest thing is, remember, it's really a confidence interval about the mean of your estimator, not necessarily about the true function. All right. I want to move on to classification, unless there's any other questions. There is an appendix, which is just, some people don't like all the asymptotic stuff. That it bothers them to see all those asymptotic approximations. You can do all these bounds and things and so on, completely finite sample. So for those of you who worry about that stuff, I put in an example of how you bound the mean squared error using only finite sample methods without asymptotic approximations. So that's just optional if you want to look at it. Good. So let's keep going. We've done linear classification, linear regression and nonparametric regression. Now it's time to turn to classification. This can be done, we can do this pretty quickly because there's quite a bit of overlap between the two, and a lot of the classifiers we use are in fact related to regression estimators. So as you all know, the difference here is that instead of predicting a real valued outcome, we're just predicting a discrete outcome. For the most part, I'm going to assume it's binary. And we're going to divide this again into two sections, linear and nonparametric classifiers. And I'll probably go through this first part very quickly because from 701 and 715, you've seen a lot of this before. Throughout, there's 4 examples we're using here, so I just mentioned them at the beginning. The iris one, I don't know why we put that in there. It's an overanalyzed data set. Have you all seen this before? There's 50 samples from 3 species of flowers, and you measure like the petals and all that stuff and try to classify them, and like any classifier will get this right. It's a really easy problem. The second one's more interesting because it's predicting coronary heart disease from tobacco use, LDL, and so on. So it's actually more interesting. And then another famous one, the handwritten digit one, is pretty old, right? You get images and you try to predict, is it a 0, 1, 2, 3, and so on. And a little more, although it's a bit old, 2004, but it's apropos for the season, political blog classification. Using the words in a blog, the idea is to predict whether it's a liberal or conservative blog. So those examples will show up. The first part here is just reminding you of stuff that you already know from either 705 or 701 or 715. If you've forgotten this, just look through the first part and remind yourself of the basic definitions. In particular, of course, the optimal classifier or Bayes classifier, remember. Well, first of all, I'm always going to use the most common risk function, which is just misclassification error. That's not a statement that you should always use that particular risk function, but I am using that one throughout the notes, and it is the most commonly used one. And remember that with respect to that particular risk function, the best classifier is based on the regression function, which is if the regression function is bigger than a half or less than a half, you classify as 1 or 0. So m of x is the mean of y given x. Or since y is binary, that's the same as the probability that y is 1 given x. So there's this intimate connection between classification and regression because the best classifier is really just thresholding the regression function. You should all have seen the proof that this is optimal, and if you haven't, it's there for you on page 3 and 4, so you should go through it if you've forgotten it, just because it's such a standard thing. And I also want to remind you of another critical fact, which is there for you to review if you've forgotten it, which is how does the risk of regression and the risk of classification relate? Which is given this form, I can always form what's called a plug-in classifier, which is to first estimate m. So we could take any regression estimator we want now that we've learned and put it in here. And that would give us a classifier. That's called a plug-in classifier. And on page 5, here's a theorem we did in 705. And if you've forgotten it, I put the proof again, which just says that the prediction risk of the plug-in classifier minus the risk of the Bayes classifier is bounded above by how well m hat estimates m so that if m hat is close to m, that's guaranteed that you're coming close to the optimal risk. But a very, very important fact to keep in mind, and we'll talk about this in more detail actually later on, is that it really is an inequality, and there are many cases when this is strictly less than this. So you can do pretty poor, this could be a pretty poor estimator of this, and yet you could still have small risk. Not the converse, but you can do pretty poor on the right-hand side and still do well on the left-hand side. That's what makes classification easier than regression. You only have to guess whether you're above it or below it, and that's what the picture, figure 3 at the top of page 6 is showing you, that if there's a well-defined decision boundary, you can estimate m poorly and still classify well. Okay? We'll make that actually precise when we talk about something called the Sibikov or margin condition. So let's just review. And if you've forgotten any of that, just go through it and remind yourself of those things. What we want to talk about now are the linear classifiers and then the nonparametric classifiers. Linear classifiers, as you know, look like this. They're linear. So we'd have something like this, a hyperplane. Everything over here would be called a 1, and everything over here would become a 0. So let's just quickly list all the ways we know of doing linear classifiers, and then we'll see if we need to go through any of the details. There's Gaussian discriminant analysis, where you treat the distribution of the x's as Gaussian. There's logistic regression. There's support vector machines. There's Fisher linear discriminant analysis. Are these all familiar? Should I review some? Okay, so that's probably the least important one. Let me click. How about if we just quickly review all of them? I was kind of assuming you knew all these, but maybe I shouldn't do that. Didn't you do that in 701, 715, all this stuff? All the linear classifiers? You did logistic and SVM. All right, so let me just quickly, we won't spend a lot of time on this. There's lots of roads to get linear classifiers, okay? Lots of things result in linear classifiers. So the Gaussian discriminant analysis, maybe you called it something else, but let's rewrite the Bayes rule a different way. Another way to write the Bayes rule is 1 or 0, but when we look at m of x, that's the probability y equals 1 given x. That's the probability, did I call it? Yeah, probably p of x times pi. I'm just doing Bayes rule here. So what this is I've just rewritten that the density of x in class 1, in other words, the probability of x given y equals to 1, I'm just calling p sub 1. And the density for x in class 0, all right, is p sub 0. And pi is just the marginal probability y is equal to 1. And so, you know, you just do Bayes' theorem to write y given x as x given, this is probability of x given y equals 1 times the prior probability or the class probability over the sum. And so saying that m of x is bigger than a half is the same, if I rearrange it now, as saying that, let me make sure I get the constant right, as this is here it is. Just saying that p1 of x or p0 of x is bigger than 1 minus pi over pi, and 0 otherwise. Right? Just rewriting it in terms of the class densities. And this is sometimes what we're about to do is called the generative approach, where we specify a full model. People call that a generative model, how you would generate the data. So the idea is we're thinking here about the x's. If you think about y as being Bernoulli, obviously, but what is the distribution of x given y? If we pretend that x given y equals to 0 has a normal, so in general that would be with mean mu 0, and then x given y equals 1 is a different normal. We now have a fully specified model. This is a generative model. I'm going to say y is Bernoulli. That's the only distribution you can have. And then x given y is a normal with a different mean, different variance. Well, I can now estimate those normals by maximum likelihood or whatever. Just put in mu hat, sigma hat. I can estimate pi. Pi is just the fraction of 1s. And now I have a plug-in classifier. That's called Gaussian discriminant analysis, because we're using Gaussians. Okay? And the form of the classifier is actually not linear, contrary to what I was aiming at. It's quadratic. This is actually called quadratic discriminant analysis, because if you plug in the normal, the classifier that you actually get, just finishing up here, is it's given on the page, theorem 4, bottom of page 6. But it turns out it's a quadratic boundary. It's just algebra. I'm just plugging in normal distributions into here and saying when does this happen? However, if you force sigma 0 and sigma 1 to be equal, if you force sigma 0 and sigma 1 to be equal, you get the equation at the bottom of page 7, which you can see, if you look at the equation, it's linear. So that's Gaussian linear discriminant analysis. And all it is I look at the Bayes rule, I notice it's a function of the densities, I estimate the densities with normals. And whether I take the covariance matrices to be the same or different, I either get a linear or a quadratic equation. And that's one of the simplest ways of doing classification. And it does lead to, in the special case, at least if equal covariance matrices, that's the simplest way perhaps to get a linear classifier. One of the oldest ways of getting a linear classifier. And of course it generalizes very obviously to k groups. You just estimate the class density for each group with a different Gaussian. So what we'll do is we'll stop there. There's an example we plotted out here what it looks like for quadratic and linear discriminant analysis for the iris data. And so then Thursday, Ryan will do something completely different. Then next week, I'm going to talk about logistic regression. Then I'm going to talk about how does that relate to Gaussian discriminant analysis. Then we're going to talk about high-dimensional sparse logistic regression, kind of like the lasso, but for classification. Then we'll do support vector machines. So that'll all go pretty quick, and then we can switch to nonparametric classification. Okay, are there any questions?
Easily translate 0 to 1 classification to 0 to 8.
Yeah, so how do you go from 0 to 1 to many classes? It depends on the classifier. So some of them are easy. So for Gaussian, it's easy. You just use k Gaussians. For logistic regression, we just replace the 1, 0 outcome with k of them. For some of them, like support vector machines, you have to write research papers about it. So it depends which classifier it is. Any other questions? All right, so I'll see you next week. But remember, Thursday, Ryan will be here. Ryan Tipsarani.